Hi everyone, you're very welcome to this lecture which will concentrate on the basics of electricity. Um, Before we start, maybe it's useful to just think of what the world would look like if we didn't have any electricity. It's fundamental to our modern society. Okay, it's hard to think of any piece of technology that can operate at all without electricity. And so an understanding of electricity is important in an understanding of technology of any description. Okay, and that goes for laptops, PCs, smartphones, all the accoutrements that you could possibly use in terms of in terms of computing. Okay, so electricity also is can be difficult for those of you that are new to the subject that haven't studied before. You may find what I'm going to go through in the next sort of half an hour to an hour quite off-putting in terms of there's a lot of jargon. We're talking about things that are absolutely tiny. What makes up electricity is electrons, and they are infinitesimally small particles. Okay, so, but just bear with it, and you'll find that as we go through the lectures, you'll find a comfort with it. You will get comfortable with using sort of the equations and determining what's going on inside a circuit. It's logical, and everything is doable from that perspective. And you'll also hopefully find the labs to help as well in figuring out how circuits work and the rest. Okay, so if we're going to talk about electricity, then we need to start at the level of atoms. I'll just share the screen with you with the set of notes that you should have at this stage. We start here with, as you can see, with the atom. Basic building block of all matter, and you all will know at this stage, I'm sure, that an atom is composed of a nucleus at the center, surrounded by orbiting electrons. Now, for many materials, those orbiting electrons are held rigidly within the atom or held in bonds between atoms. But a crucial thing to remember is that for certain materials, and particularly metals, or definitely metals, some of the outer electrons, maybe one or two per atom, can actually drift away. And you can see in the diagram that's displayed there, I've shown a set of atoms with individual electrons that are just floating around. Those individual electrons can move. And in any general wire, they are moving sort of all the time. Even something like, I've got an old iPhone charger cable here. Inside that, first of all, what you see in the cover is a plastic covering. It's not the electrical cable. Inside that, you'll see metal wires, at least two of them. And why you need two, we'll explain later on. Okay, and they're moving in random directions. For example, if I hold it vertically, some electrons are drifting upwards and some electrons are drifting downwards, and they're drifting all over the place randomly. Okay. And if I draw this on the board beside me here, just to probably can see there. If I draw it on the board, we can represent the metal as regular arrangements of atoms, as you've seen in the booklet. With the individual electrons marked in as minuses, just randomly throughout this, that they're not particularly attached to any atom, and they're moving randomly around the place. Okay. So nothing much is happening in this charger cable as at the minute. Now, what things become interesting when we apply a bit of an electrical force or an electrical pressure that causes things to move, all the electrons to move in the same direction. And you can think of this quite simply as if we put a large plus over here and a big minus here. And then from what you understand of charges, you should see that all the electrons will tend to move towards the positive. Okay, and when you have electrons all moving in the same direction, you have current. You have effectively electricity. Okay, so just to say a word, first of all, about charge. Each electron carries a tiny bit of charge. And we call the charge on an electron little e. And it is what, well, it's, first of all, it's minus because it's a negative charge, 1.6 by 10 to the minus 19. Very, very small number, you know, 0.18 Okay. And the unit that we measure charge in is the coulomb, named after a French scientist, capital C. Okay, and 1 coulomb of charge, because each electron carries such a tiny proportion of charge, 1 coulomb involves something like 6 billion electrons. Okay, so if we introduce this positive and minus, we get electricity to flow, and we have a thing called current. Now the symbol for current is capital I, and current equals the charge traveling divided by time. Q is the symbol for charge, T is the symbol for time. And we measure current in amps. Again, that's short for ampere. Ampere, a name of another French scientist involved in the early development of electricity. So if we have 1 coulomb traveling past a point in 1 second, then we have 1 amp of current. Remember, 1 coulomb means 6 billion electrons passing a point in a wire in a second. So huge numbers of electrons to give you an amp. Okay, so an amp is a decent, is quite a large current. So the symbol for current is I, and its unit is shown as capital A, ampere. Okay. Now, in terms of this plus or minus, what drives the electrons? So the electrons are driven by obviously that change in that charge there. Sources of that pressure to push electrons around the circuit are referred to as EMFs, electromotive forces. Okay, so let's just put it back. EMFs, electromotive forces, come from a variety of things. You have the sockets in the wall, you have batteries. I have some rechargeable batteries here that are sources of EMF. And also you have power supplies, which you'll use in the lab, or power supplies. Okay, they come in different sizes, and they are not just when I say different sizes. Physically, you can have batteries smaller than this. You can have button cell batteries. You can have batteries that are rectangular blocks, and you can have the large sort of battery that you have in a car. Okay, so the car battery gives you the electrical pressure coming from an EMF or a source of EMF is measured in volts. So a battery like this, each one of these batteries produces 1.2 volts. Their little rectangular power pack batteries produce 9 volts generally, and the battery in a car is about 12 volts. Okay, so that's a measure of the pushing power, the electrical pressure that will be applied that causes electrons to move in a particular direction. Okay. And what does that mean? If a battery is rated at 1.5 volts, 1.5 volts, what does that mean? Well, that means, again, we come back to this idea of a coulomb of charge. That means for every coulomb of charge that goes through the battery, the battery will add 1.5 volts. 1.5 joules of energy to it. And what tends to happen is if you've got electrons going around in a circuit, so it leaves the battery here, goes round, goes through some sort of piece of equipment, for example, a resistance or the element of a kettle, and it comes back to the EMF source having lost all its energy. Then every coulomb of charge going through picks up, like we say, 1.5 volts, and then it goes back through the device again, loses all its energy and comes back, and then it gets more energy. And it just continues on in that cycle. So try to remember that volts means what a battery of 9 volts means that every coulomb will get 9 joules of energy. It will lose those 9 joules of energy as it goes around the circuit and then picks up the extra energy again back in the battery. Okay. Now, as it was mentioned, as the electricity goes around the circuit, it loses energy. And we call that electrical pressure. That thing that changes as it loses energy as it goes around the circuit, so therefore it's losing that electrical pressure. We call that potential. And as electricity goes around the circuit, it loses potential. It drops in potential, so that when it gets back to the circuit, or back to the battery, or back to the EMF, it has 0 potential left. That the unit for potential is also measured in volts, the same as EMF. Okay. And I mentioned the circuit a few times. A circuit is one of the 2 things you need in order for electricity to flow. You need a continuous loop, which is what we call a circuit. So if you're into Formula 1 racing, you have a circuit, you always come back to the start. So it's a linked path all the way around. So you must have a circuit, and you must have a potential difference. Because we talked about potential already, but there must be a difference in potential, and that's what drives the electricity to keep moving, move around the circuit. Okay, so moving along, we can now look at circuits and circuit diagrams. So generally when we draw circuits, this is circuit diagrams are a simple way of demonstrating what circuits look like. Where did you there? I skipped something. Okay, so potential difference drives current. So it kind of should be, if potential difference drives current, what happens if we increase potential difference? Well, you increase the force acting on the electrons, you make them flow faster, and so you have a bigger current. And we end up, that can be summed up with a thing called Ohm's law, which says that the potential difference is proportional to the current. Or maybe more correctly, the current is proportional to the potential difference. Okay, we can write that simply as V is proportional to I. Potential difference is proportional to current. So the potential difference is measured in volts. The current is measured in amps. That proportionality sign, it's not an equation. It's a mathematical relationship, but it's not an equation. You can always replace the proportionality sign by an equal sign if you include a constant. So this is generally written as V equals IR or V equals RI. So R is the constant that we introduce. And it too is an important quantity in electricity. R is resistance. And it is the property of a circuit which resists or opposes the flow of current. Okay, so the bigger the resistance is, the smaller I will be. Effectively, if you have a low resistance, you will have a high current. If you have a high resistance, you will tend to have a low current. Okay, so we have resistance. It is measured because of Ohm's law. The symbol for resistance, or the name of the unit for resistance, is ohm. Okay, so in honor of Georg Ohm, the unit is the ohm, and it makes kind of sense that we have a letter omega, so that is the symbol that is used for resistance. So it's measured in ohms. That is capital omega, by the way. Lowercase omega is a kind of curly W, so we use the capital version of that. Okay. So just to recap where we are now in terms of the symbols and the units. So V is potential difference, capital V. Always use capitals for these, potential difference. And it turns out that that's measured in volts. Then we have I, which is the current flowing, and that is measured in amps. And finally, we have R, which is resistance, and that's measured in ohms. Okay. And Ohm's law, V equals IR, is the centerpiece of this part of electricity that we're going to be covering in the next in your lectures in the module. Okay, so V equals IR, we'll be using it all the time. It's deceptively simple, and it takes a bit of practice getting used to, but once you get on top of it, then you should have no problem with you shouldn't have too many difficulties with doing the exercises and doing the labs. Okay, so that's the fundamentals of it out of the way. We now look at sort of circuit diagrams and move on to doing a lab. Okay, so circuit diagrams first. I'll just take you down here. I mentioned already that electricity is a very logical field. And you should never, if you're in a lab and you're setting up an electric circuit, you should always be entirely clear about what you're being asked to do. Everything is directed by what the circuit diagram tells you. You have to be able to read the symbols in a circuit diagram, but outside of that, it is completely logical. So we start off with symbol for a battery or a source of EMF. Just to say at this stage that there are two kinds of sources of EMF. You have AC and DC. For the vast majority of this module, we'll only be considering DC sources. We will mention AC later on. DC stands for direct current, and that means that the current is going to flow in the same direction around the loop, around the circuit all the time. So the symbol for DC, you have a short side and a long side. Why do we need that? Well, a DC has a plus side, which is the long, and a negative, which is the short. Okay. These lines represent, so that's the source of EMF. It could be a battery. It could be in your lab experiments, it'll be the power supply. Okay. These lines are, I've drawn them all crooked, so I better just maybe do a better job of that. These lines represent the wires that you use. Now, when we have a connected circuit, you'll have current flowing, and you may want to measure the current. We measure the current in what's known as an ammeter. Basically, it's an amp meter, but it's spelled ammeter. So you're measuring the current flowing through there, and it's labeled, the circle labeled as A. The current has to flow through it in order for it to be able to measure it. Then you have a resistor. Now, the resistor is either shown like that, or it is shown like that. In your typed notes, I always use this diagram because it's much easier to draw a rectangle than it is to draw a zigzag like that. Okay, but if you look in textbooks, you're as likely, if not more likely, to see that representation rather than that one. Okay, so just be aware both are used. Right. And I'll finish off the circuit there. So in this circuit, this is the positive. Current will flow along from positive through the ammeter, through the resistor, and back to the negative of the battery or the power supply or whatever we're using. One other thing I can add on to this circuit is a voltmeter. And I would recommend that if you're attaching a voltmeter to a circuit, always add it on at the end, after you've completed the circuit loop, the current loop. Okay, so what does it do? Well, it measures potential difference. It's labeled with a V because potential difference is measured in volts. And it's called a voltmeter, something that measures volts. So what it does is it picks up what's the potential there and what's the potential there. And the difference between the potential at those 2 points is what you get displayed here. Now, when I say potential, I mean, remember what that is. It's the energy per coulomb. The electricity, the current comes out of the battery with a certain amount of energy per coulomb, a certain amount of potential at a certain potential. That potential remains constant all along a normal wire, and then it loses its energy as it goes through the resistor. So it goes into the resistor with a high potential here, and it comes out with a lower potential here. And in fact, by the time it gets back to the battery, it's 0 volts. So therefore, all along this wire, it should have a potential of 0 volts. Okay. So that's the basics of it. We have our EMF, we have a potential difference, we have a current flowing, we have a resistance, we have an ammeter to measure the amps flowing, we have a voltmeter to measure the volts of that potential difference. Okay, so there's in the notes there is a particular example given. And just pull that up now just to show you what I'm talking about. I'm going to display it briefly, and then we'll talk about it in a bit more detail. So a simple circuit. And you're asked to calculate the readings on the voltmeter and the ammeter for the circuit below. So it's basically what I've drawn on the board here, but just particular values on it. Okay, so we'll stop sharing and we'll go back to the diagram I've drawn on the whiteboard. We'll go back to this diagram. We'll pick some values then. So we're told in the question, this is a 5-volt battery. And we're also told that the resistance here is 200 ohms. All right. Now, I'm going to make some changes. I'm going to get rid of the ammeter for a second. Okay. And I'm going to redraw this now. And I'm going to use, hopefully, I know some of you may not be able to see this. I'm drawing this with a red pen. Okay. And what I want to represent here, maybe I just use some green for those of you that can't see red. The current goes along here, down here, and into the resistor. This is a 5-volt battery. The current out of the battery, the potential along here is going to be plus 5 volts. That's the energy of the current as it goes into the resistor. When it comes out of the resistor, it's attached to the negative of the battery, and everywhere along that wire has energy of 0 joules per coulomb, or 0 volts. Okay. And what this voltmeter here reads is the difference between the potential there and the potential there. So the potential at that point is 5 volts, because everywhere along this wire is at 5 volts. The potential there is 0 volts. Everywhere along there is 0 volts. So that's 5 volts, that's 0 volts. This gives us a reading of the difference between the two. And so you'll get a reading on that display there of 5 volts. I can ask some different questions. For example, if I connected a voltmeter between there and there, what would it read? Well, if you think of it, the temptation maybe is to say 5 volts, but if you think about it, the voltage there is 5, the voltage there is 5. What's the potential difference between those 2 points? It's 0. So the reading on that one is 0. And if I do the same over here, maybe it's obviously much easier maybe for you to see over here. That's also 0 volts. Okay, and really in a circuit, you tend to only pick up a potential difference when you connect it across a device. Now, one thing you could say to me is, well, how practical is this circuit? Well, in many ways, this circuit is the basis of of most electricity, most devices that you use. A couple of simple examples would be the basic structure of that circuit is what you get with a kettle, an oven, a hairdryer. I mentioned AC and DC. They all tend to operate off AC supplies, but the principles are the same. You have current flowing, you have a resistor, and the current loses energy as it goes through the resistor. Okay, and also you can see that loss of energy for something like a toaster. The reason why the wire glows red hot in a toaster is because the electricity loses its energy as it passes along the wire. Okay, so that is the visible loss of energy. In the labs and anything, we won't be going anywhere near anything red hot or that. If you do the experiments correctly, the resistances shouldn't get warm, but the electricity going through those resistances is losing energy. Just be aware of that all the time. Okay, so back to our question. What can we say? And in your notes, there are a few sort of the general points that are made that are really, really important to keep in mind. Current flows from plus to minus. That is always true. Having said that, that is always true. But having said that, electricity is made up of electrons. And as you may, if you think about it, electrons are negatively charged. They'll be attracted to the positive and repelled by the negative. So in fact, although I will always say electricity flows from plus to minus, the electrons themselves, the things that are moving that make up electricity, actually go from minus to plus. Okay. That will come into play in some elements of maybe a module you might be doing next semester, but it won't be an issue for what we'll cover in this semester. But always think that the current flows from plus to minus. The current has the same value for this particular circuit, and for many circuits, the current has the same value everywhere. I know we talked about the current here losing energy as it goes through the resistor, but you can think of that as a electrical energy. It doesn't change how fast the electrons move. So the electrons, there's as many electrons moving here as there are there. So the current is the same everywhere. Can't be any other way. So the current is the same everywhere. So that's why we only measure the current at one point in the circuit. Because if we know the current there, we know the current everywhere else in that circuit. The potential at the negative of the battery is always zero. The potential at the positive of the battery is whatever the battery is. So if it's a 9-volt battery, this would be plus 9 volts. If it's like a lithium-ion battery that you might have in your laptop, varies maybe as it discharges from about 4.4 down to 3.6, something like that. So say 3.6 volts would maybe a typical value. So if it's lithium-ion, 3.6 volt battery, the potential here will be 3.6 volts. Okay, all points linked by a simple wire are at the same potential. So all the points, all the lines that I've drawn in red are at plus 5 volts potential. Okay, all the points there linked by that black wire there, black line there, are at 0 volts. So if they're connected by a simple wire, they're at the same potential. Looking at this voltmeter again, we can see the potential there is 5, the potential there is 0, and so the potential difference is 5 volts. The ammeter, I'll just put it back into our circuit again. The ammeter, which measures current has to flow through the ammeter. So it's directly connected into the circuit. All right. So current, it's part of the loop that the electricity flows through. The voltmeter is what we say is connected in parallel. That means the current flows that way. It doesn't flow through the voltmeter. Okay. And to finish off this section, we now just need to apply Ohm's law. So I might just redraw the diagram again, smaller version of it. So we have a 5-volt battery, an ammeter connected to a 200 ohm resistor. 5 volts. I haven't drawn the different colors this time. So we know the reading on voltmeter is 5 volts. What current have we flowing? Apply Ohm's law, our basic equation for electricity. V equals IR. So for this resistor, we have 5 volts across it, so V is 5. We have R is 200 ohms, so we know that and that work out I. So V is 5 volts, R is 200 ohms. 5 equals I times 200. 5 over 200 equals I, which equals 0.025 amps. Another way of writing that size of amps, and you'll find that a lot of the currents that we'll be measuring in the lab are small. So that is 25 milliamps, 25 thousandths of an amp. Okay, so I'm just going to stop there. That basically just goes over the basics of electricity: potential difference, current, resistance, and Ohm's law. And then a little bit about understanding how circuits work. Okay, so I'll just leave it there and I'll come back with a shorter video looking at resistors in series and parallel.